James Webb stared at a patch of sky smaller than a grain of sand held at arm's length, and in that tiny sliver of darkness it found thousands of galaxies. Some of them are so far away their light has been traveling since before our sun existed, and several of them should be impossible. We'll go to the edge of everything we can see. We'll meet galaxies that break the rules, black holes that grew too fast, and a force pushing the universe apart that no one fully understands. If you enjoy the journey, like and subscribe. It keeps these going. Prepare yourselves. We begin. The image loaded on a screen inside NASA's control room, and the scientists stared in silence. It was July 2022. The James Webb Space Telescope had just sent back its first deep-field image, a tiny, almost empty-looking patch of sky, so small that a grain of sand held at arm's length would cover it. Inside it, thousands of galaxies. That alone would have made headlines. But almost immediately, researchers zoomed in and noticed something wrong. Big, bright, fully formed galaxies were sitting in the frame that, according to every model scientists had spent decades building, had no right to exist that early in cosmic history. Here's how the universe is supposed to work. After the Big Bang, hot gas slowly clumped under gravity into the first stars. Those stars died and fed new generations. Over hundreds of millions of years, small galaxies merged into bigger ones. A slow, gradual build, like a city growing from a dirt road. Webb found skyscrapers on that dirt road. Galaxies so massive and structured they looked billions of years old. Except the light arriving from them had left when the universe was only a few 100 million years old. About 2% of its current age. Scientists didn't panic. They went quiet, then went back to their computers to check the math. There was no simpler explanation waiting for them. A physicist named Alison Kirkpatrick, who had spent her career building the very models Webb was now challenging, said openly that she was having a crisis of faith. Webb was built for exactly this kind of look. It sits nearly 1 million miles from Earth at a gravitational sweet spot that keeps it perfectly still. Its mirror spans almost 21 feet, about the height of a 2-story building. It sees in infrared, wavelengths invisible to human eyes. And on its first real look into deep time, it broke the rulebook. Light travels fast, but not instantly. So looking far away means looking into the past. The sun is 8 light minutes away, so you see it as it was 8 minutes ago. Webb points at galaxies billions of light years away, meaning it sees light that left them when the universe was a baby, only a few 100 million years old. As the universe expands, it stretches light, like drawing a wavy line on a rubber band and then stretching the band. Light from the earliest galaxies has been stretched so much it has shifted completely out of the visible spectrum into infrared. That's exactly what Webb was built to catch. A mirror coated in gold, which reflects infrared exceptionally well. Shielded by a sunshade the size of a tennis court to keep the instruments colder than almost anywhere else in the solar system. It has to be that cold, because infrared is essentially heat, and any warmth from the telescope itself would drown out the faint, ancient signals it's trying to hear. Like trying to hear a whisper across a football field while standing next to a jet engine. What that whisper revealed: galaxies that were already enormous, organized and packed with stars at an age when they should have been messy newborns. In early 2023, a team of astronomers published a paper whose title alone caused a stir. They had found 6 massive, well-formed galaxies existing when the universe was only 500 to 700 million years old. One of them held roughly 10 times the number of stars in the entire Milky Way, a buildup that took our galaxy billions of years, apparently done in a fraction of the time. The lead researcher, Ivo Labbé, put it simply: It was like running a census and discovering the newborns weigh the same as the adults. For a galaxy to get that massive that fast, it would need to form stars at an extreme, sustained rate, thousands of solar masses per year, when a normal mature galaxy like the Milky Way manages 1 or 2. There's no known mechanism that allows that. Normally, when stars ignite, their radiation pushes back on the surrounding gas and slows further star formation. A natural break. Something let these galaxies skip the break entirely. Picture the early universe as a city under construction. You send a drone to photograph the site after just 1 week of building. You expect concrete foundations, maybe some steel beams. Instead, the drone comes back with photos of finished skyscrapers, windows, lobbies, people already inside. That's the scale of the shock these galaxies produced. One follow-up study, hunting specifically for the most extreme cases, found an object that, if the measurements hold, contains a stellar mass equivalent to roughly 100 billion suns. All of it assembled when the universe was less than 700 million years old. That single galaxy demands a star formation process so efficient it borders on physically unreasonable. And yet, there it is, leading ideas for how this happened. The very first generation of stars, hypothetical, never observed population 3 stars, may have been massive and hot enough to seed rapid growth. Or dark matter clumped differently in the early universe, pulling gas together faster than models allow. Nobody has a clean answer, and it's not just 1 or 2 outliers. Webb keeps finding more of them, batch after batch, and researchers have started calling it the galaxy overcrowding problem. The early universe looks more populated than the venue was ever built to hold. Before Webb, cosmologists were quietly confident in a framework called the lambda-CDM model. Tested for decades against the cosmic microwave background and the distribution of galaxies we see today. It predicted small, messy, irregular young galaxies in the early universe, with big organized spirals, like the Milky Way only appearing billions of years later. The model sets a mathematical limit on how much mass a galaxy can accumulate by a given point in cosmic history. Webb's galaxies blow past that limit, some by a small margin, some by a factor of 10 or more. Researchers cross-check the data obsessively against other telescopes and different analysis methods. The galaxies stayed massive. The violations stayed real. Imagine a recipe that says a cake takes 4 hours to bake. You pull it out after 30 minutes, and it's perfect. That doesn't mean you got lucky. It means something is wrong with the recipe. Cosmologists are now debating whether the early universe had conditions we don't understand, whether assumptions about dark matter are off, or, more provocatively, whether the age of the universe itself might be wrong. Oxygen, carbon, silicon, iron, heavy elements that only get forged inside stars generation after generation, over hundreds of millions of years minimum. Webb found galaxies less than 1 billion years old already showing oxygen levels close to what we'd expect in much older galaxies. That means multiple generations of stars had already been born, lived, died, and enriched their surroundings, in a fraction of the time that should take. One idea. Those first, massive population 3 stars burned through their lives in just a few million years, seeding galaxies with heavy elements at record speed. It helps explain the chemistry, but it adds even more pressure to an already impossibly tight timeline. For about 380,000 years after the Big Bang, the universe was an opaque fog. Then it cleared, leaving behind the cosmic microwave background, the oldest lights we can see, smooth and almost featureless. Then came the cosmic dark ages, 100 to 200 million years, with no stars, no light, just gas slowly gathering under gravity. Then the first stars ignited. Cosmic dawn, and Webb was built to catch it. What it found, those first stars, likely hundreds of times more massive than our Sun, poured out radiation that stripped electrons from surrounding hydrogen gas, a process called reionization, far faster and more intensely than models predicted. The universe's lights came on faster and burned brighter than anyone expected. An engine running at full speed with no warm-up time. At the center of nearly every large galaxy sits a supermassive black hole. Ours, Sagittarius A star, contains about 4 million solar masses. Some of the black holes Webb found in the early universe contain hundreds of millions to billions of solar masses, and existed less than 1 billion years after the Big Bang. Black holes grow by feeding, and there's a natural speed cap on that feeding called the Eddington limit. Feed too fast, and the black hole's own radiation blows away its food supply. Running the math at that limit, growing a small seed black hole up to 1 billion solar masses takes roughly 1 billion years of near-constant feeding. Some of Webb's black holes existed at 400 to 600 million years old. The math doesn't close. Black holes grow by pulling in gas and dust, which heats up into a glowing disk called an accretion disk, bright enough to outshine the entire galaxy around it. A black hole feeding this way is called a quasar, and Webb has spotted quasars from so early in cosmic history that their host galaxies were barely formed, yet the black holes at their center were already monstrous and already feeding at full capacity. One of the most extreme examples existed when the universe was only about 400 million years old, under 3% of its current age, already carrying roughly 1 billion solar masses. The available time simply isn't enough. Possible explanations: direct collapse, black holes, where a massive gas cloud collapses straight into a black hole without ever forming stars first, giving it a giant head start, or repeated mergers stacking mass quickly. Each idea requires its own new assumptions, and Webb keeps finding these oversized black holes in numbers too large to call them rare flukes. Hiding among the same era are the so-called little red dots, tiny, intensely bright, compact objects scattered across Webb's deep fields that don't cleanly match either a normal galaxy or a standard quasar. The leading guess is a massive, actively feeding black hole wrapped in a dense shell of dust, glowing in infrared. But there are too many of them for the numbers to work cleanly, which means either an unknown, widespread phase of black hole growth or something the standard model doesn't include at all. Galaxies aren't scattered randomly. They sit along a vast structure called the cosmic web. Filaments of dark matter along which gas flows and collects into clusters, with nearly empty voids in between. Webb has found large, organized protoclusters, dozens of galaxies already clumping together, less than 1 billion years after the Big Bang, and filaments already laid out in patterns the models say shouldn't exist yet. Webb has also caught galaxy clusters in the act of colliding in the early universe. Collisions where the galaxies themselves mostly pass through each other harmlessly, since the space between stars is so vast, but the hot gas clouds surrounding each cluster slam together at millions of miles an hour, creating a shockwave that separates the visible gas from the invisible dark matter. It's the same effect famously seen in the nearby Bullet cluster, and finding it this early adds one more layer of structure that shouldn't have had time to form yet. At the same time, some regions are far emptier than they should be. The Buta's Void, discovered in 1981, spans about 330 million light-years, so large that crossing it at the speed of light would take 330 million years, and contains far fewer galaxies than statistics predict, even for a region that size. Webb's early universe surveys keep finding voids that are both larger and emptier than expected, as if matter evacuated those regions faster than gravity and dark energy should allow. And when researchers map how these voids and dense filaments are arranged across hundreds of millions of light years, the pattern isn't random. It has a direction to it, a preferred axis the standard model never predicted. Scientists measure the universe's expansion rate, the Hubble constant, in two independent ways. From the nearby universe, stars and supernovae, and from the ancient cosmic microwave background. The two methods disagree by about 8 to 10%, a gap called the Hubble tension. Before Webb, some hoped better data would make the tension disappear. Instead, a team used Webb's sharper infrared vision to recheck the nearby universe measurements from scratch. And the disagreement held. It isn't a measurement error. The universe is genuinely behaving in a way that one, or both, methods fail to capture. One suspect: dark energy. The unknown force making up 68% of everything that's accelerating the universe's expansion might not be constant after all. Webb's data, combined with a separate survey called DESI, hints that dark energy may have been stronger in the past and is weakening now. If confirmed, that alone could help explain the impossible galaxies, the reionization excess, and the Hubble tension all at once. Because a universe with a stronger early push would have had more energetic, favorable conditions for fast structure formation. If dark energy weakens further, gravity could eventually win and slow the expansion. If it strengthens instead, the far future holds something called the Big Rip. An acceleration so extreme it eventually tears apart galaxies, solar systems, and even atoms. Neither has been confirmed, but for the first time, precise enough data exists to take the question seriously. The standard age of the universe, 13.8 billion years, comes from multiple independent measurements that all agree, until Webb's impossible galaxies made a small but serious minority of cosmologists ask, what if there's simply more time than we think? One astrophysicist, Rajendra Gupta, proposed in 2023 that a revised model incorporating changing fundamental forces could push the universe's true age to as much as 26.7 billion years, nearly double. The response was skeptical. Changing the universe's age would mean re-explaining dozens of independent measurements that currently agree, and that's an extremely high bar to clear. But the fact that the question is even being discussed seriously in published papers, not just hallway speculation, shows how much pressure Webb's data has put on the standard timeline. A more mainstream version of the same question doesn't touch the age at all. Instead, it asks whether the early universe simply had different conditions, perhaps tied to that same, possibly changing dark energy, that let structure form faster without needing extra time. In this view, the clock stays the same length. It's the story of what happened inside that clock that needs rewriting. Either way, something in the current picture has to give. Using a technique called gravitational lensing, where a massive foreground galaxy cluster bends and magnifies the light of something far behind it, exactly as Einstein's relativity predicts, Webb detected the most distant individual star ever seen. Nicknamed Earendel, its light left it when the universe was only about 900 million years old, roughly 12.9 billion years ago. It appears to be an extremely massive, extremely hot star, possibly with a close companion. And its chemistry shows it isn't a first-generation star at all. Even this early, the gas it formed from had already been enriched by an earlier generation of stars that came and went in the blink of a cosmic eye. Webb has also used lensing to find fully formed spiral disk galaxies far earlier than models allow. Thin, organized, orderly structures that should require billions of years of settling to form, existing when the universe was less than 2 billion years old. Something protected them from the violent mergers that should have disrupted them. Smooth, cool gas inflows or unusually gas-rich, self-stabilizing disks. Either way, it means the calm conditions needed to eventually build something like our own solar system may have existed far earlier in cosmic history than anyone expected. There's a quieter assumption buried underneath all of cosmology, that the universe is isotropic, that it looks statistically the same no matter which way you point a telescope. No preferred direction, no special axis, just an even symmetric cosmos in every corner of space. Without that assumption, the math of the Big Bang becomes vastly more complicated. With it, everything stays clean and manageable. Several independent surveys, both before and after Webb, have been quietly chipping away at that assumption. Galaxy spins, which should be randomly split between clockwise and counterclockwise, show a small but consistent preference for one direction in certain patches of sky. The expansion rate itself appears slightly different depending on which direction you measure it in. And a peculiar alignment in the cosmic microwave background, nicknamed half-jokingly the axis of evil, lines up in a way that shouldn't correlate with anything in the nearby universe at all. None of these signals is enormous on its own, but multiple independent teams using different instruments and different methods keep landing on the same faint asymmetry. Webb's ultra-precise mapping of distant galaxies is now feeding into that picture too. And if the universe really does have a preferred direction, the implications ripple all the way back to whatever produced the Big Bang in the first place. Some physicists take that question seriously enough to ask whether the Big Bang was truly the beginning of everything, or a transition, a bounce from some earlier state. In these models, faint imprints of what came before might still be hiding in the cosmic microwave background, the oldest light we can observe. Webb doesn't study that background directly, but every precise measurement it makes of early galaxy clustering narrows down which of these pre-Big Bang models are even possible, ruling ideas out one by one. A stranger related idea rides along with certain versions of inflation theory, that our universe might be one of many, each with its own laws of physics, forever beyond direct observation. Nobody expects to prove this outright, but as Webb's data increasingly favors specific inflation models over others, and some of those models naturally predict a multiverse as a side effect, the idea moves slowly, cautiously, from pure speculation towards something resembling indirect scientific evidence. Dark matter and dark energy were once treated with the same suspicion, and both are now accepted because the indirect evidence became too strong to ignore. Webb wasn't only built to look backward in time. It also reads the atmospheres of nearby exoplanets. When a planet crosses in front of its star, some starlight filters through its atmosphere before reaching us, and different molecules absorb different wavelengths of that light. By analyzing which wavelengths go missing, scientists can work out what a distant atmosphere is made of. In 2022, Webb confirmed water vapor around K2-18b, a planet roughly 700 light-years away, sitting in its star's habitable zone, the range of distances where liquid water could exist on the surface. It also picked up a tentative, unconfirmed signal for dimethyl sulfide, a molecule that on Earth is almost exclusively produced by living organisms, mostly marine phytoplankton. The signal is weak and needs confirmation. Webb has also confirmed carbon dioxide in the atmospheres of several rocky worlds in the TRAPPIST system, a group of 7 planets orbiting a small star about 40 light-years away, several of which sit near the habitable zone. No single gas proves life oxygen and methane can each show up without biology involved. What scientists are really hunting for is a combination of gases that shouldn't coexist stably unless something is actively replenishing them, the way life constantly replenishes Earth's atmosphere. Webb can't quite read a rocky, Earth-sized planet's atmosphere in that level of detail yet. The signals are too faint and too easily lost in the noise. But it proved the detection method itself works, moving the search for life from pure philosophy into instrument design and observation scheduling. Webb is the proof of concept. The next generation of telescopes, built specifically to hunt for the chemical fingerprints of life, will pick up where it leaves off. Impossible galaxies, oversized black holes, a broken timeline for heavy elements, a reionization era running hotter than predicted, a Hubble tension that won't close, voids too big and too empty, disks too orderly too soon, little red dots nobody can classify. Individually, any one of these would fuel years of debate. Together, they're arriving faster than the normal, careful process of science was built to absorb. Researchers have checked for calibration errors, a systematic offset in Webb's brightness measurements that could make distant galaxies look more massive than they are. That effect is real but small, and it doesn't make the core discrepancies disappear. What's unusual is how openly scientists are living with the uncertainty. Publishing the disagreements, debating them at conferences, admitting in public that something is wrong with the model without yet knowing what. And Webb is still only scratching the surface of its own data. It produces more processed images and spectra than the world's astronomers can examine in real time. A growing archive of light nobody has looked at closely yet, some of which may hold the most important discoveries Webb has already made without anyone knowing it. The next generation is already being built around what Webb found: the Nancy Grace Roman Space Telescope, designed to attack the dark energy problem and the Hubble tension with a field of view 100 times wider than Webb's. The extremely large telescope in Chile, with a mirror roughly 6 times Webb's diameter, and a proposed habitable worlds observatory aimed squarely at reading the atmospheres of Earth-like planets for signs of life. Webb was launched partly to confirm a story scientists already believed they understood: small, messy proto-galaxies slowly building up into the mature cosmos we see today. Instead, it came back with a different story: skyscrapers where there should have been foundations, monsters where there should have been infants, a universe that grew up faster, brighter, and stranger than anyone had modeled. Webb didn't answer the oldest question we've ever asked, looking up at a dark sky. But it changed the terms of the debate, and it showed over and over that the universe at its edge is not quiet, not empty, and not simple. What it found is going to take the rest of this century to understand.